Here it is. Okay, so we stopped before when we were talking about the lump plasticity with finite length and fiber cross-section. Now the next step is to show you the other alternative way of doing lump plasticity. This time is the classical lump plasticity, so the zero length lump plasticity, where basically you have an elastic section like this, an elastic element that spans the entire length of the element, and the nonlinearity will be lumped into a zero length interface. In OpenSees, it is called zero length element, which is basically a spring. Okay, so it will be very similar to this one, but without the finite length. This basically implies something, that the response that we will assign to the nonlinear zones here will not be, like in this case, a moment curvature, but it will be a moment rotation. And to show you something else, instead of using a zero length that has a fiber cross-section, we will use a zero length with a phenomenological spring, moment rotation diagram, okay? The disadvantage of that approach is that you don't have the coupling between the axial force and the bending moment. The advantage is that it is much faster, of course. And if you don't have information about the fiber cross-section, you can directly input the moment curvature. Now, in this example, if you remember before, we extracted the moment curvature at this point, and we copy-pasted it here. So in this example, I will show you how to use the typical model that people use in OpenSees for lump plasticity in terms of moment rotation, which is the modified Ibarra-Medina-Kravinkler model. And when I will send you all the files that I'm using, you will also have this support Excel file that basically has this moment curvature extracted from our fiber cross-section. So this is the moment curvature for that specific level of axial force, okay? So of course, one assumption is that when you use the lump plasticity with a phenomenological constitutive model for moment rotation, you cannot expect an interaction with the axial force. So in this case, we are directly computing the moment rotation for this specific value of axial force, okay? So in a while, I will show you the parameters that you need for the modified Medina-Kravinkler, but basically here, I already computed some of them. Now, the first thing that I've done, let me show you, let me remove this value here, so I will show you why I added it. Okay, so this one is the stiffness, the initial stiffness taken from the first 2 points of the moment curvature. So in this case, it has stiffness in terms of moment and curvature. Then I have the length of the plastic zone, because I will have to convert the curvatures to rotation later on. And then I fixed a couple of points. So the first point is arbitrary, you can choose it, and is the first point that that basically defines the initial point of the first hardening. Then the second point under moment is computed as the maximum of the moment here. Let me see, I have something in the chat. Okay, I don't see the chat now for some reason. Just a second. Okay. Okay, back to the screen. So the second point is the maximum moment. Then we have the residual moment, which is once again arbitrary, this value. And then these values of the curvature are, some of them are custom, you can choose it. Some others are computed, like this one, the first one. Then for the Kravinkler model, we need to define some values which are the curvatures of these points. And these ones are computed automatically in the script. Basically, these ones give me the abscissa point of this curve in terms of curvature. And then I will convert them to rotation by simply multiplying them by the plastic hinge length. So I consider this curvature constant over the plastic hinge zone. One extra thing that I have here that we will be using for the Medina-Kravinkler model is the hardening ratio. which is automatically computed and depends on the initial stiffness. Now, before going ahead, I think I changed, no, I didn't change it. Okay, perfect. In this example here, when you take the stiffness from the moment curvature, it will give me the exact elastic stiffness of my cross-section in terms of moment and curvature. But since this one is zero length interface, and since the elastic response is already given by the entire beam, it is better to consider this one some order of magnitudes larger than the elastic stiffness, in such a way that it doesn't go up with the elastic response of the rest of the element. That's why I took this one and I multiplied by 100. It doesn't need to be extremely large, just a couple of order of magnitudes more, because it is connected in series with the elastic beam. Okay, so here we have all the input values. Now let's go back to the solver. Oh, for some reason I see the menu bar. Just a second. Okay. Oh, it doesn't disappear. Well, I don't know how to make it disappear. Okay. Okay, perfect. Sorry, but this is the desktop remote, and sometimes I have problems with this. Perfect. So let's go back to the preprocessor. Once again, I need to copy another beam here. So I go in geometry, copy. I select this one, and I copy it once again, let's say here. Now we go in property. As we did before, we need to orient this one as well. So drag and drop the local axis, so it will be oriented. Once again, we copy the boundary conditions, as we did before. So you can edit the fixity, and we add this point to the selection. So fixity is over the 3 points. Vertical load as well, edit and add this point. And the impose displacement, same thing. Select this point, okay. Okay, so boundary conditions are correctly applied onto the third and last element. Now we need to go back to the properties and we need to change it. Of course, now I copied this lambda approach finite length, so it has the same properties now, and I have to change them. So this one, as I said, will be a 4-node element actually. So 2 nodes for the internal elastic beam, and then 2 extra nodes that will be connected through springs to the internal element. Now this is quite annoying because every time you have to do this kind of zero-length plastic hinge approach, you always need to duplicate nodes and to create some springs between them. Since it is quite annoying and time-consuming, we decided to create an automatism in STKO. So we basically create just one line, as we did now, and we have a particular section property that will, during the writing of the electrical file, will take care of writing 2 extra nodes and creating the spring between them. So you don't have to do it, okay? This one will be very easy. If instead you want to do the same manually in OpenSees, keep in mind that you have to create 4 nodes. Okay, but this topic is about STKO, so I will show you the easy way. So the elastic section, we will use the same one that we used for the finite length, so we don't need to redefine it. What we need to define now is the uniaxial material for the spring about that we will use it for the moment rotation about the z-axis of the local coordinate system of the beam. So we go under physical property, we click add, and we can call it moment rotation spring. And as I said, we are going to choose under material, and this time it is a uniaxial material. It is under other uniaxial materials, and it is called modified Ibarra-Medina-Cravinkel with pinching. Otherwise, the peak oriented, which is slightly different. Well, actually, the difference is in the cyclic behavior, but in this example, we are not going to do any cyclic behavior. So here we are going to put all the input points that we have in these Excel files. So the initial stiffness that was 3.93 to the power of 15. Then we have the strain and hardening ratio at this point, which is 1.89 e to the minus 6. Same for the negative part, because with the Medina-Kravinkler model, you can do something that is different in tension and compression. But in this case, it is symmetric, so we use the same. These two values are positive always. Instead, the moment, my and my plus or negative, they should have the proper sign. So 3.3 to the power of 8 in the positive direction, and minus 3.3 to the power of 8 in the negative direction. Then you have some parameters for the cyclic behavior. If you're interested, you can go and see the Medina-Kravinkler. It has many parameters. Many of them are used for the hysteretic curve. And in this case, we don't need it because we're not going to do any cyclic tests. So we use some default values here, which is 0.4, 0.4, and 0.1 for pinching. Then these other lambdas here will be left at 0. These values as default are fine. And then the theta P and theta PC, you can see here what they mean, but they're basically, they're basically these parameters here. And I already calculated into the Excel file here. We are going to use the one in rotation, as I said. So for plus and negative, we use the same value, which is 0.00579. And same thing in the other direction, 0.00579. Then the post-cap plastic rotation, which is 0.525. Same thing on the negative side. Then the residual ratio. This one is a ratio between the initial moment, this one, the ones that determines the end of the elastic part, the ratio between the residual and over the initial one. So the residual in this case is slightly higher, that's why the ratio is 1.05. Okay, so same ratio, 1.05 in the positive part and in the negative part. 1.05, 1.05. Then we have the ultimate rotation. Now, since we don't want to make this curve drop to 0, we put a very large ultimate rotation. Okay. And these are few other values for the degradation. We actually don't need it, so we keep it to 0. Now, if we want to do a simple monotonic test, just to make sure it is equal to this one, we can push it to 0.5 is the last one, 0.6, for example. Okay, but probably it's too much, 0.1. Okay, so this one is the same curve that basically we have here. Yeah, in this case, I push it up to 0.05. Yeah, 0.525 as ultimate rotation. So if you want to make sure, 0.0525. Okay, so this is the same curve we have there. So this is fine. But this is just one spring. So for 1 degree of freedom, which this one will be the spring about the z-axis. Now, all the other degrees of freedom, because of course here we have to link 6 degrees of freedom, they will be continuous. So to simulate a continuity, we use a very kind of stiff uniaxial model. Let's call it stiff. Make sure you don't make it too stiff, because if it is too stiff, the entire stiffness matrix will look like singular. So we go on the uniaxial, we choose some standard, and we choose an elastic behavior. And here I've chosen, let me see the value for the elastic one, which was stiff material 1 to the power of 13. Okay. So basically now we have two springs, one non-linear and the other one which is linear and very stiff. Now we need to combine them into the zero length material. The zero length material is basically, let's call it moment rotation spring 6 DOFs. This one is basically you go under special purpose, zero length material, and here you have the material for the zero length section, for the zero length element. When we go here, you first have to choose the dimension. In our case, we are doing a 3D. Then the model type, we have 6 degrees of freedom, so U are displacement rotation. And then you have the option to choose one or many, here it's called direction, but they are the 6 degrees of freedom, okay, in the local orientation of the beam. Now, if you leave some of them unchecked, it means that you're creating a release about that axis, okay? Now, in our case, we don't want to create any release. We want to use something for all the degrees of freedom. And they will be completely fixed. So we use the stiff for continuity in all of them, but the moment about the z-axis. So we use the stiff everywhere. And in the 6th degree of freedom, because of course we have 3 rotation, x, y, z, and 3 translation, sorry, and 3 rotation, x, y, z. So in the last point here, we use the moment rotation spring, because, why? Because the local axis, we go and see here, has the z-axis pointing in this side, okay? So remember that here, the direction are in the local orientation of the element. So the nonlinear behavior will be the moment rotation about the z-axis. Perfect. Okay, so now this one is the material model for the zero length. But as I told you, we are not going to create the zero length manually. We are going to create something which is an automation that we have in STKO, which is called the hinged beam. The hinged beam is not actually an element that is in OpenSees. In OpenSees, there is not this element, but it is an automation that we have in STKO that automatically creates 4 nodes and 3 elements. The internal one, which is the elastic one, and the 2 zero lengths, okay? But for the ease of creation, here we created this automation. Okay, so let's call it hinged beam property. We go under special purpose. Well, basically every time you have to find something that is not in OpenSees, it will be under special purpose. And we have hinged beam. Hinged beam, PP stands for physical property, because then we have the same one for the element property. Okay, here basically it says, okay, give me a physical property for the internal beam. And here we choose the elastic beam, of course. And then give me the zero length property, so the spring, in the first and second end of the beam. And we choose the moment spring 6 DOS. Okay, so here we have basically 3 materials, 1 for the internal element and 2 for the 2 interfaces. Okay, perfect. And now we can drag and drop it to this element. Okay, now as you can see, the representation is slightly changed. This representation with a fake shrink. This one is it's not physical, but it's just for visualization. It is telling you that here and here you have a zero length with some kind of release or spring in general. Perfect. Now we need to do the same in element properties. Now we have a nonlinear force beam column. Now for this element, actually, we need 2 kinds of elements: the elastic beam column for the center and the zero length. So we first create the elastic beam. The elastic beam element is faster than the generic beam element because it doesn't have, since it assumes its behavior is elastic, it doesn't have integration points, so it is automatically integrated. So we go under beam columns and we choose elastic beam column. We don't need to choose the elastic force beam column. There is no need here. So the elastic standard displacement based beam column. Here we just need to say that it is in 3D, and eventually, if we want to use a linear kinematic or one of the 2 nonlinear kinematics. And in this case, we are just using linear kinematics, so it is okay. Now we don't need to assign this to anything. We just need to define it. Now we need to define an element for the zero length, and we can call it spring element. We go under model, once again, zero length element, and we choose the standard zero length because you have many of them. The zero length for contact, zero length for section, for interfaces, but we just need the zero length, plain zero length. And we just need to tell him that it is 3-dimensional. Okay, so that's fine. And finally, we can create our hinged beam element, which is a combination of the 2. So hinged beam, we go under special purpose. Where is special purpose? Special purpose, hinged beam. Now this one basically is saying it's pretty similar to the engine beam physical property. So it says, okay, give me the element, the finite element that you want in the middle. In this case, we want an elastic element. And tell me the elements that you want in the two ends. And we want the same kind of element, spring element, zero length, simple. Okay, now it's this one that we can drag and drop here. Because as I said, even if in STKO this one looks like just one single element with two nodes, when it will be sent to OpenSees, it will be actually three elements with four nodes. So one internal element and two springs. That's why we have to do these steps here. So we are fine now. We've just created the physical property and element property. Boundary conditions are the same. We already transported them onto the other element. So we can just go to mesh. Once again, since I changed the geometry, I need to rebuild the mesh. And now you can see that in STKO, we just have 6 nodes and 3 elements, okay? As you may expect. Now we will see that instead in the TCL file created for OpenSees, you have more nodes. You have 2 extra nodes and 2 extra elements, okay? So let me save this one. And in the meantime, I run the analysis. Okay, it will be pretty fast. Now, when the analysis is running, I want to show you what this automation has done. So as you can see, here in the mesh, okay, this is fine. Okay. Here in the mesh it was saying 6 nodes, 3 elements. Now let's go and see what's going on here instead. We go in our file. If we go on the nodes, we have 6 nodes only. That's fine, because these are the 6 nodes we have in OpenSees. But then if we open elements, here we see that we created the standard element of before, and then 2 extra nodes created for the zero length. This one will be automatically created by OpenSees. They are not by OpenSees, by STKO when it is writing the input file for OpenSees. So it creates these extra nodes, then creates the elastic beam column between the extra nodes, which are the internal one, and then connects these nodes to the real nodes that were available in STKO by means of a zero length, where the materials are the ones given by our physical property. Okay, this is pretty nice because doing these things manually takes a lot of time. Now this is a simple column, but imagine you have to do this one for an entire building. It takes a lot of time to duplicate the nodes for every element, and this tool is quite useful. Okay, so now we can go to the post processor and we can reload the database. Okay. Now here we have the section fiber. Of course, the fibers are only in these 3 elements. This one instead, of course, doesn't have any fiber. Here we can remove this one because now we need to extract the data also from this other element here. So let me show the node. Then I want to select, in this case, actually, I don't need the fiber plot. I just need the surface color map. Okay. So I go under extract data, and we want to make sure that the response of this element is compatible with the others. So we go on nodes, next, second stage, displacement versus reaction force in X of the top 3 nodes. Now here I can just use a rubber band selection because I had 1 node in STKO and 1 node in OpenSees. Here, however, I have to pay attention. Here, I don't have just 1 element. In fact, if I go here and I click, it says, oops, you have 1 element here, which is the zero length, and 2 nodes. Which one of them do you want to select? Now, here we want to select the node that was already available in STKO, which is the same node in which we applied the load. So it is the node with the lowest ID, which is node number 6. The node number 8, instead, it is located at the same location, but as I told you, is the extra node created for the interface. So we choose node number 6. We go ahead, we have all the 3 selections, next. We call it FU, and we want to keep multiple results so we can overlap them. And this is what you obtain. As you can see, they are perfectly matching. Of course, the green one overlaps better with the red one, which is the one here, because they share the same elastic reduced bending section here. And of course, here you see how you can get the peak strength, because of course we calibrated it on the moment curvature obtained from the distributed approach. So they are pretty the same. Of course, now if we run the same analysis, but we change the level of vertical force, we will see that the results are not the same, because the first two approaches have an interaction with the axial force. This one instead it is not. It is just pre-computed based on the previous value we had on the axial force. Okay. So the huge advantage of using this third approach is that you don't have fibers, so the computation will be faster, and you have a less impact on the size of the database. Now in this case it is a small model, but imagine for a large model. The disadvantage is that you lose any coupling between the moment in each direction and the coupling between the moment and the axial force. So I would say probably the best compromise is the one in between here, of course. Well, that's fine. So let me save this file. So this one is all for the beams. Okay, so now let's say if you have some question about this topic, and then we will move on to the next topic, which is modeling of reinforced shear walls. Now this one will be made on shells, so we will introduce some extra concepts, and we will talk about the constitutive model we have in 3D. So I will anticipate probably some notes about this model now, because they are common to both reinforced concrete and masonry. Okay. So before going ahead, but if you have any question, please. Let me see the chat if someone has questions. For some reason, I stopped sharing so I can see the chat, because for some reason I don't see. Okay, I have it here.
Hi, Massimo. Good morning. Can you hear me?
Yeah, I can hear you.
Okay.
Fabio.
I'm Fabio, and I wanted to ask you a question which is more general, not referring to the beam that you have modeled right now. I can start the video. Okay. And so I saw that you can actually use the MTCO recorder, which is the one made on purpose for STKO. But
yeah.
What if we want to write like a user-defined recorder for some reason that someone want to output the default that OpenSees uses, like writing, you know, a node, recorder node, etc. And the second question was like, can you decide with STKO to only run the analysis without writing first the tackle files? So you only run tackle files that are already in a folder. Okay.
Okay. Both questions can be answered with the same tool we have in STKO. I will talk about this tool in the second, where we will be doing the shear wall, but I can anticipate it. So let me share my screen, and I will give you the answer. And this is the same I will do in the next example. Now, as you can see here, all the analysis steps that I've done, among which, of course, you have the recorder, are predefined analysis steps. Now, of course, you may ask, as you asked, what if I want to use something that is not supported in STKO? This is a perfect right question. Why? As I said, STKO is a user interface for OpenSees. We support pretty much everything. Of course, for the recorder, we support only our own recorder because it's the only useful for us. But we understand that if you have your own version of OpenSees, it may happen that you have something that our STKO is not aware of. First point. Second point is that OpenSees is scriptable, so you can do everything. And for STKO, it is impossible to handle every possible combination that you can do with Tcl. So every time you want to do something which is kind of particular and which is not directly available in STKO, you can go under miscommand always here, analysis steps, miscellaneous commands, and you choose custom command. Custom command is basically a tickle script. So you go here and you write something. Like now in this example, let me call it, for example, recorder, some custom recorder, and then you put some input data, okay? Now this one will be your tickle script. It can be complicated as you want. In fact, in the next step for the shear wall, I will show you how to do an adaptive tab stepping. So here you can write the entire tickle that you want. You press OK. Okay, and now if I run this analysis, now I don't want to run it, of course. I just want to write the input file. I want to show you something. I just created this new analysis step, which is the custom one, with that script at the end. So if I go in my RC column and I go under the analysis step file, I will find exactly the script that I put in the exact position where I put it. So let me open it. And if I go, okay, if I go to the very end, here I have my tickle script, okay? Now, for example, since it is a recorder, I don't want it here. I want to move it just after my MPCO recorder. I write again the input file. I go back here. Okay, this one has changed. Reload it, and now it is placed actually at this position, just after the MPCO recorder. So whenever you want to write something like standard recorder or anything else that is not in STKO, you can just use the custom tickle script. This is better than just writing the tickle file, because when you write the tickle file and you modify it manually, then the next time you will write the tickle file, your modification will be lost. So when you want to write something custom, do it with the custom script, because at least it will remain there. Now, to come into the second question, you said, okay, but let's say I have an already handwritten tickle file, and I just want to use the MPCO recorder, and I want to run it from STKO. This is the same thing you can do. For example, the first thing you do is to create an MPCO recorder, okay, like this. Then here, you just create just one analysis step, which is the miss command, and here you can copy-paste all your tickle file, okay? For example, you have a particular tickle file that then sources other tickle files. You put it here, just after the MPCO recorder, and let's assume now this scripts, loads everything, creates your model, runs the analysis. You don't need to create anything else, so no geometry, nothing, just the recorder and the miss command with your tickle script. You can run the analysis now. The important thing is that the recorder should be defined before, of course, because it will record everything defined by your analysis, okay?